Okay, so I want to talk about selected topics in quantum cosmology, from Einstein to Everett to de Wit to others, and back means back to Einstein, as we are going to see. So first, let me remind you of some of the things that Einstein thought about quantum mechanics, not well-known things. I mean, there are well-known debates, Einstein-Bohr, but there are deeper things that Einstein said about quantum mechanics. In particular, there is a famous, I mean, not so famous discussion between Einstein and Heisenberg, just after Heisenberg found quantum mechanics, where Heisenberg said that he was just imitating Einstein in discussing only observable things, that he was not interested in the quantum reality, but just, numbers you could measure in experiments. And he said, but you, Einstein, introduced that in special relativity. And then Einstein said, not at all. From a heuristic point of view, it could be useful to remember what one is really observing, but at the level of principle, it is erroneous to found a theory uniquely on observable quantities. It's exactly the opposite thing. It is only the theory which decides what can be observed. And this lesson of Einstein had been learned from general relativity, because at the beginning of the discovery of general relativity, there was a lot of confusion, because there were things like coordinates, time, t, things like that, and people were confused because in special relativity, t was time, pure and simple, while t meant nothing in general relativity. And then, after some confusion, it was learned that it is the mathematical formalism of general relativity which gives meaning to what you observe in the end, and you don't care about what is tx. You will get the meaning by looking at the theory. And this lesson was confused at the time by some people, like Painlevé, for instance, who insisted that one should impose like a neo-Newtonian way of thinking about space and time, and that was the wrong thing, okay, which confused things. And part of the aim of this talk is to say that, in my mind, the Copenhagen interpretation is a kind of neoclassical interpretation of quantum mechanics, where instead of taking, like Everett told us to do, at what the mathematical formalism of quantum mechanics is saying about reality, you try to impose old classical ideas. Now, that was the first reminder about Einstein on quantum mechanics. The second reminder is the last talk that Einstein gave in his life, the last seminar, on April 14, 1954, in Princeton. And the whole talk was mainly about quantum mechanics and a little bit about general relativity. And in it, he expressed again his discomfort, not his opposition, but he also said, I believe that quantum mechanics describes the world and is essentially, for all practical purposes, things. But there is something that I find strange, that it's difficult to believe that the description given by the wave function is complete. It seems to make the world quite nebulous unless somebody, like a mouse, is looking at it. And so that was the first remark. The second, and this remark struck Everett, because it was then. And the second remark, at the end of his talk, he said, Einstein, there is much reason to be attracted to a theory without space and without time, which is a vision that we should have theory without the concepts of space and time, which I find remarkable that in 1954 Einstein was thinking about theory without space and without time. But nobody has an idea how to build it up. And that will be, I will come back to that at the end. So Everett, at the age of 23, Everett, attended Einstein's last seminar and was struck by the sentence of Einstein on the mouse and the universe. A few months later, so that was April 54, he was there in Princeton. He also attended lectures by Niels Bohr in Princeton and discussed with the assistant of Bohr, Petersen, Age Petersen. We became a friend at the time. And then, in a flash of intuition, he had the idea of his new way of thinking about quantum mechanics at the end of 54, seemingly. But it took him some time to publish his ideas because first he looked for an advisor. He was advised to ask Wheeler because people said Wheeler can give you a thesis in a short time. But in that, he went to Whiteman, by the way. And then Whiteman told him first thing, yes, I would be very glad to give you a thesis, but you have to notice that all my students never got their thesis in less than 7 years. Then he started saying, okay, thank you. And he went somewhere else. But actually, it was not such a good idea because Wheeler then started saying, interesting, but what will Bohr think of this? You have to change the words. I will ask Bohr. Okay. And then there was a kind of cabal in Copenhagen. In particular, Rosenfeld started doing calumnies really on Everett and trying to destroy things. So there was so it took time for his thesis to exist. And you know, the thesis was reduced by a factor 4 from the initial thing because Wheeler said, no, you have to take this away, take that. And then there was a little thing published in 1957. But what is the motivation of what he wrote at the time? The motivation is how is one going to apply the conventional formalism of quantum mechanics to the space-time geometry itself? So this is why here I mean, Everett's view is I think, granted by most people working in quantum cosmology, and there is a reason for that. It was in part motivated, from Everett's point of view, by thinking of how to describe a quantum space-time geometry, especially in the case of a closed universe. The citation here not put is to Einstein. And because if you have a closed universe, especially compact universe, there is no place to stand outside the system and to observe it. Okay? And this is taken from his paper here. And this paper proposes to regard pure wave mechanics, that is to say just the Schrödinger equation without anything else, without collapse of the wave function or whatever, as a complete theory, just for people who have never heard of Everett. The idea is you just take quantum mechanics as is, just the basic Schrödinger equation, nothing more. And you postulate that the wave equation satisfies a linear wave equation everywhere and at all times. And this provides a complete mathematical model for every isolated physical system without exception, including the whole system. The wave function is taken as the basic physical entity with no a priori interpretation. Interpretation comes only after an investigation of the logical structure of the theory. And here, as always, the theory itself sets the framework for its interpretation. So I don't know from what Everett got the idea, but this is the same type of idea that, I mean, Einstein, I told Heisenberg, I forgot to say that when Einstein told Heisenberg, you should look at the formalism because it is the formalism which decides what is observable. A few months later, Heisenberg wrote that. While discussing with Bohr, he remembered the sentence of Einstein, and then he discovered the indetermination, the uncertainty relations, because he understood what part of the formalism was giving something linked to observable. So that was a useful role of Einstein. And so that was the first part of our story about quantum cosmology and Everett, is that Everett had the idea of application to quantum cosmology when he built his views. Now, the first important player in the question after Everett on quantum cosmology and quantum gravity is Bryce DeWitt. So in his paper, which was published in 1967, and the preprint that I have a copy of the preprint of April 1966, and as you know, very short, Wheeler played a role there also because Wheeler wrote like a 200-page preprint, putting everything, the canonical theory and then the relativistic theory, including what became later the Fadeev-Popov ghost and all that, in one big paper. And the referee for Physrev, who was Wheeler, sat on the paper for 2 years and told him, no, you have to cut your paper, it's too long. And in the meantime, Fadeev-Popov published their thing, and then Wheeler published 3 papers, but after Fadeev-Popov. Sorry? DeWitt, sorry. No, but Wheeler was the referee. Yes. DeWitt then lost, and then DeWitt published, yes, sorry. Okay, now this is taken from the preprint, and again we see this sentence that is going through this field. The formalism itself determines its own interpretation, but this was already in Everett and in Einstein. This idea, which seems to crop up in general relativity more than in any other theory, has been stated in its most drastic form by Everett, connection with quantum mechanics. So here is summarizing Everett, and here there is a hint of what will become later decoherence, which was also already in part, but in vague part in the mind of Everett. Because of its inner complexity, the universe has a wave function which automatically splits into a stupendous number of branches, each one of which corresponds to a classical universe. This classical universe essentially move independently of each other. Everett had used at a few places the word to split. We'll come back to that. The splitting processes go on continuously, each one providing a mathematical model on a local scale of the statistical nature of quantum mechanics. So this is the main point that Everett purported to prove in his thesis, which is that the statistical aspect of the quantum mechanics is contained without assuming it from the Schrödinger equation. And here, by the way, it is summarizing this. The statistical interpretation of the wave function emerges from the Schrödinger equation itself without having to be imposed from the outside. Within each branch, various automata, e.g. human beings, because this was, Everett then learned his life in doing operational research for the Pentagon, and he had worked on game theory. So for him, it was clear that he had to make a model, like von Neumann also, of a human being as an automaton. And the question is then, what will these automata record, and what can they communicate about the contents of the memory banks? And then here the wit is summarizing what I had said, so that you get this way the statistical nature of physical phenomena. Okay, and maybe this footnote is useful also. Needless to say, to one who finds the size of the actual universe, that is to say, the universe around us, cosmological universe, frightening, Everett's conception must appear vastly more unsettling. And I know that many people find it unsettling, and I want to ease your way to think about Everett, if possible. So, speaking of quantum cosmology, I want to explain, by the way, everything I will say is at a very elementary and pedagogical level, just to, because I realized by discussing some people that not everybody knows the Wheeler-DeWitt equation, things like that. So I will explain basic things and elementary things. So one idea is what Wheeler called superspace, which is the arena of quantum cosmology. So each point in this space is supposed to be a spatial geometry. Like, for instance, especially if you think of a cosmologically evolving space-time, at one moment of time, defined arbitrarily, you have a compact space with some, a lot of geometrical structure, a bump of curvature here and there. At another time, you have a bump. And then all those things, they depend how you slice classical space-time here. Anyway, you defined a formal space where each point is a spatial geometry, okay, a 3 geometry. And in principle, you want also a geometry, that is to say, you want to caution by the fact that if you apply a diffeomorphism, it will be the same geometry, even if in coordinates the components of the metric look different, it's still the same geometry. The quotienting will be done in later. So this is the picture that Wheeler gave in some books at the time, and I also remember that I met Wheeler here in 1973. 73, yes, I was 22, and Wheeler gave a talk in the other building, and in his pictures they were this. He was visiting IHS at the time. So this is, each point here is a moment of the history of a cosmological space-time. A classical space-time would be just a line or like a leaf, which is the class of equivalence of the various slicing. So that would be a classical. A quantum space-time will be a wave propagating in this space, okay? Because each point of this configuration space is a space, a geometrical space. Now, this comes to this metric representation that of quantum gravity that Wheeler favored at the time. It's no longer a representation which is used by people trying to develop quantum gravity because it has technical defects, but it's useful conceptually, and we are going to use it here. So what is it? The idea is that instead of having the wave function, which usually for a particle, the wave function is a function of the configuration space of the particle. So 3 coordinates for one particle, 6 coordinates for 2 particles, and things like that. Here you want a wave, a complex number, which is a function of a geometry, because a geometry at one moment is the configuration of the evolving geometrical space. If you had a scalar field, we were talking about the field representation of quantum field theory, where you have a wave functional, that is to say, a function of the state of the field all over space at one moment of time, the field and not its conjugate momentum. So you choose here, you know, there. Classically, you could measure phi and the conjugate momentum in space, pi of x, but quantum mechanically, you can depend only on phi of x. And here is an explicit example that Wheeler liked, which is easy to derive. If you think of the usual vacuum state of the ground state for the electromagnetic field, okay, in infinite space, then if you describe usually in quantum field theory books, the field, the electromagnetic field, is decomposed in harmonic oscillators, modes. Then the wave function would be the product of all the exponential minus 1/2 q square, which is the omega q square, which is the wave function of one mode. Then you make the infinite product of this. But the modes are the Fourier transform of the field, so you can re-express that as a wave function of the field. And then you find that this explicit expression, it is a quadratic form in the magnetic field, which is gauge invariant, at 2 points with a kernel, which is 1/x square, okay? So it's an example of a wave functional for a particular state. For a different state you will have, of the geometry, you will have something. Now, as I said, you want to impose that this thing is invariant under diffeomorphism. If I apply a spatial diffeomorphism, it should be the same number associated to a geometry. And therefore, you have to impose a condition which comes from this diffeomorphism invariance, which is that when you do the functional differentiation of this function of the geometry with respect to the metric at one point of space, so it's a function of the spatial coordinate point x, this should be covariantly divergence-free, okay, with respect to G. Now, the basic point is now, so these are part, so what I just wrote is part of the Einstein's theory of gravity, because of its diffeomorphism invariance. The dynamic is only contained in the constraints, things that must be 0. And as a consequence, there are 2 basic constraints, one which is linked to diffeomorphism invariance, which I've already written down, and the other one which is linked to invariance under arbitrary time shifts, okay, that I can move the slicing of space-time up or down, the many-finger time of Wheeler. And as a consequence, you have the so-called Hamiltonian constraints, which in classical terms would be something quadratic in the momenta, the momentum coordinates associated at each point of space to the metric, Gij, that can vary at each point of space. So classically, the momentum would be essentially like the time derivative would be g dot, because the Einstein-Lagrangian is quadratic in derivative. The kinetic term is like a metric dot square with some small subtlety. So when you quantize the theory, you are going like the momenta, you replace them by derivative with respect to the configuration space, like Schrödinger did for particle mechanics. Here, the momenta must become functional differentiation with respect to the local variation at one point of space of the metric. And therefore, the classical Hamiltonian constraints, which is something quadratic in these momenta with in front something which is now called the DeWitt metric in the space of metrics. So it's a metric in superspace. It's a metric which locally gives the distance between 2 close metrics, okay, spatial geometries. So you have something pi square. So here, okay, this is like Schrödinger equation, you know, p squared over 2m plus v, the potential. But from Einstein equations, you find that the potential is minus the curvature scalar of the 3 geometry, okay, this thing, which is an explicit local functional of g and these two derivatives at one point. So at the end, this equation, which is called the Wheeler-DeWitt equation, although it was the DeWitt equation that it derived, but people attach the name of Wheeler also to this equation. As DeWitt said, the perpetuum mobile of physics, Wheeler, because they met in an airplane, I mean, between two airplanes, they met, and DeWitt showed the equation to Wheeler. He said, that's very interesting. I've been looking for that for years, and okay. So this equation is given this functional of a geometry. It's a functional differential equation which contains two functional derivatives with the metric, with some contraction. It has to be satisfied at each point of space, and then a potential, which is this 3 curvature. And this is for pure gravity. If you add matter, which is what you need at some stage, then you add also the Hamiltonian for matter, and then the equation is this. Note that this equation is not like the Schrödinger equation IH bar d by dt of psi equal h psi. It is h psi equals 0. So there is no time there, okay? There is only, it's like a zero energy Schrödinger equation. We'll come back to this. But if this is again the representation of Wheeler's superspace, now I said before, first in this superspace, space of metrics, you have to think that there are boundaries of singular metrics. Like for instance, in cosmology, we talk about the Big Bang, things where space crushes down to one point or maybe a very singular kind of limit, while there are other geometries where space is regular, it's just bumpy and arbitrary. So in this full space, there is like somewhere the boundary of singular geometries, okay? And then this Wheeler-DeWitt equation is like a wave equation in this space. And we are going to see that actually it is a Klein-Gordon type equation in the sense that it has a negative sign for some directions, and so it has a wave. That's why it can be h equals 0, because it contains in itself, it's not a positive definite operator, okay, even in a high frequency regime. And therefore you have to think of solutions of this functional differential equation as waves propagating among all geometries. And then the question will arise soon, what happens when this wave goes to the boundary? Are there boundary conditions near singular geometries? In fact, here is a list of issues in quantum cosmology that I will not discuss in full details, but the first is there a boundary condition indeed that in a sense, because part of the motivation, I mean, Wheeler's motivation was that he understood at some point that collapse, gravitational collapse, you know, things discovered especially by Oppenheimer in 1939, that when you exceed the maximum mass of a neutron star, a mass of neutrons, a number of neutrons, find no equilibrium state, no ground state. Classically, it collapses, it creates a black hole, and inside the black hole there is a big crunch singularity. The hope was always that quantum mechanics, like quantum mechanics, had helped what happens near the 1/r singularity of an hydrogen atom. Instead of collapsing to the center, you have bound states there. Maybe there is something that quantum mechanics will help. And in this context, DeWitt was the first one to suggest that maybe a boundary condition such that the vanishing of the wave functional at the singular boundary would be a nice boundary condition, but you have to prove the compatibility with the equations. Then there were speculation early on by Einstein first, because at some point Einstein said the only question that interests me is whether God had any choice. That is to say, is there a unique solution to the full to be found theory of the universe? Wheeler took it up, and more recently Hartle and Hawking made a precise proposal, I mean semi-precise proposal, because this was in Euclidean quantum gravity using formally Feynman representation, so it's not really well defined. But the idea that in a sense the wave function of the universe should be unique and should be a kind of ground state for the entire universe in some sense. I already mentioned whether quantum effects can lead to singularity avoidance at a Big Bang, at a Big Crunch, singularity. I already also mentioned that we have like the Einstein-Schrödinger equation is like a zero energy equation, no time, no energy, just zero. So where does time come from? Usual, what people call time. So it's a problem which is heavily discussed. What is the link between here? There is a complex number, a functional thing. What is the link with probability? Is there a probability interpretation of this formal thing? Okay. And at the end, is there a quantum to classical transition? I mean, here we are using Everett. There is just quantum, no collapse, no observer, whatever. At what point should we introduce the idea, or should we, which is what I think that the present cosmological universe is the ultimate Schrödinger's cat in need of an Einstein's mouse to exit its quantum fuzziness? We are the quantum mouse. Now, as Misha Gromov left, we can identify human beings with monkeys and mice. He won't complain. Quantum origin of the large scale of error. Now, I want to give a few selected results linked to quantum effects in cosmology, or really quantum cosmology. One of the important solid results is the theory first done by Slava Mukhanov and Chibisov in 1981. Slava Mukhanov will talk next week, so we'll probably mention this again in more details. I just give the idea. It's the theory of quantum perturbation as just the linearized level of a classical background, which is an inflationary cosmology. So here you make two approximations. You treat space-time, there is a classical background, then you add quantum fluctuation, you treat only linearly. But when you do quantize a geometry of this type, and here in inflationary cosmology, the matter content which drives the expansion, the exponential expansion, is a scalar field with a certain potential, so it makes energy density in the universe, but the scalar field evolves in time, gravity evolves in time, and there are fluctuations. And Slava Mukhanov and Chibisov found that if you define a certain variable, gauge invariant variable, which is a combination of the fluctuation of the scalar field and some variable which comes from the geometry, this satisfies like a mode, a separated quantum mode, which then you can quantize in the usual way of quantum field theory in time-dependent external space-time. Here it is taken for a flat space, which is a good approximation of our space, spatially flat in space, but not in time. And then you have the Heisenberg Dirac relation. A dagger is a delta function. And then this gives, later from this, you can compute all the correlations about density fluctuations and things like that. And this agrees very nicely with what we observe in our universe. And therefore, we should think that the origin of all the matter which exists in the universe, matter fluctuations, is quantum. And I will come back to this. Eta is a conformal time, so instead of dt, which I did not write, it's dt divided by a, so that the background is conformally to Minkowski. So it's this dt divided by this scale factor. Now I want to discuss another topic where here it was quantum effects in cosmology, in a background with gravitational quantum fluctuations. Evidently, the idea of Wheeler, DeWitt, and Everett was to go beyond, to treat really full gravity as not a classical background, but as a quantum object. And to do that, I will first discuss the simple but instructive limit of so-called mini superspace, which was after the initial work of DeWitt, mainly pioneered by Charlie Misner in 1969, and then there are thousands of papers on this. So this is, you take the system of gravity, Einstein's theory, coupled to, let's say, a massive scalar field, okay? But immediately you reduce this system. This system has infinitely many degrees of freedom. Gravity can have fluctuations, the scalar field can have fluctuation, but you assume first classically that gravity is homogeneous in space, so that in space it is a three-sphere omega 3 with a uniform scale factor of expansion. So there is only one function which is the scale factor which describes gravity. And correlatively, you assume also that the scalar field is homogeneous in space, so that the energy density associated to the scalar field is also homogeneous and can sustain this thing. This reduction is consistent at the classical level. And then you quantize the dynamics of A and phi after this reduction. Okay? So this is an approximation because you don't take into account the back reaction, second order effects and higher order effects of quantum fluctuation on the background. It's an approximation, but it allows to discuss something which is quantum. And when you do that, so you plug this ansatz in Einstein's Lagrangian, and you quantize after that, and you do the Hamiltonian transformation. And then you can write the Wheeler-DeWitt equation, which is just the Hamiltonian constraints, but where you have transformed the moment. For instance, A, which is the scale factor, will have a momentum associated, canonical momentum, pi A, and then this pi A you represent by h bar over I d by d A, okay? And this is the way the pi square in Wheeler-DeWitt equation becomes this term, second derivative with respect to the scale factor. The kinetic term pi phi or phi dot square of a scalar field becomes d by d phi square. The mass term m square phi square becomes multiplied by a volume factor, a cube and then another thing, it's a4 here. Here I have put a cosmological constant, lambda times the volume of space, it gives lambda a4. And then there is this term which is the R3, because remember in the Wheeler-DeWitt equation there was pi square, there was the curvature of free space, R3, minus with a minus sign, and here the free space is a free sphere with curvature plus 1 over a square. And this, so you change sign, so it becomes minus the curvature 1 of a free sphere divided by a square multiplied by a4. This is why there is this minus lambda a square. So you get finally a PDE, I mean a differential equation in two variables, the geometry A and phi. And if you introduce, this is like an ordering, there is a problem of ordering, okay? These operators, functional differentiation, you have to define. There is also the whole theory of renormalization, which is hidden in the fact that you make products of singular operations at the same point of space. So that's why this program was a bit stuck for doing real quantum gravity. But for these models, it's okay, it gives an idea. And if you choose this ordering constant like p equal 1 here, and if you replace A, which is the scale factor, by its logarithm, let's call it alpha, then you find that this equation, this is the way you see, it's a Klein-Gordon equation now. In this mini superspace, I have one direction which is for the scale factor of the universe, and one direction for phi. And this one of them is time-like, the other one is space-like. Actually, we will see that the space-like is the matter one, phi, and the volume factor of the universe is time-like. It should be with a so this is like time, this is like space, and then you have a potential which depends on the two variables. So at least it's a well-defined thing. You could say, now I have PDEs, what are the solutions, what do they say about what happens at the singularity, and many people discuss many things. In particular, you can introduce, sorry it's not very clear, but I will explain. You can introduce the idea that the universe could be quantum created from nothing, okay? This idea was first introduced by Tryon, Fomin, then there was a paper, I tried to reread it, but it's quite obscure what they tried to say by Bart, Angler, Gunzig, and then Vilenkin introduced precisely what I'm talking about here, is that if you use the equation which was on the previous transparency, this one, you write this potential. Here I have suppressed the scalar field, just pure gravity, but with a cosmological constant. You find that the potential as a function of A is something which is plus a square linked to the curvature of space minus lambda a fourth linked to the cosmological constant. So, and you must solve the Schrödinger equation. So it's a Schrödinger equation in the variable A. So you look at it and you say, okay, I can solve qualitatively the Schrödinger equation because we know if I have a potential like that, it is a tunneling effect because I want the zero energy equation. Okay, I have Schrödinger equation for zero energy, so I have to draw the energy level here, and I find this is a forbidden region where the wave function will decay or grow exponentially. So, for instance, And large universes, like our universe, like the de Sitter solution, which is de Sitter solution is a classical solution of Einstein equation with a cosmological constant. It's a big universe which goes to a small ball and then goes. This is a wave which goes like that and like that here, quantum wave. But here you can think that maybe you can tunnel having something which starts from this region and then decays exponentially and then come out as a tunneling wave function. This would be a universe which starts from zero size, so no universe at all, and then a universe exists after that. So at least you see that conceptually you can do interesting things, okay? Now, here these are where the mini superspace. But once you have the mini superspace, this quantum geometry of space and time, you can try to add more and more modes, more and more degrees of freedom. And for instance, this was done by Halliwell and Hawking, where taking a Friedman model, but with perturbations. Now you take into account that the geometry is a three-sphere, a round three-sphere, plus infinitely many perturbations of the three-sphere. So you put the full possibilities. There is an infinite sum over modes parameterized by this. And then the wave function, you find that the equations you can approximately, anyway, this is not really a factorization, but yes, because these modes are independent, you can write the wave function as the wave function that would be in absence of the modes plus an infinite product of all the wave functions for all those modes. And then you can try to write the equations for these modes and you find whether they are amplified or not. And you can, this way, recover the kind of result that I was talking about from Muranov.
That should be a butterfly function.
No, here it's alpha phi is still here. So this thing is an approximation. Because the equation, no, it's just because, sorry. Here you decompose, is just an orthogonalization of modes, okay? This is a special, it's one solution of the thing where because there is an infinite number of equations. I wanted to say that just to say that you can go beyond one thing. You have an infinite number of conditions, and among the solutions, then you can make superpositions. You have these product things. Anyway, it was not used. Let me mention another interesting idea that came from mixing quantum effects and cosmology. This is the idea of eternal chaotic inflation. Yes, I wanted to add more names here, but maybe they are enough, because it was found in various frameworks. For chaotic inflation, I think it was first found by Andrei Linde, but it was found for non-chaotic inflation by Steinhardt, Vilenkin, Guth. So the idea is the following. What is inflation? Inflation, if I view it classically, is to say at some point in the early history of the universe, the spatial geometry is driven by the presence of the energy linked to a scalar field, which is displaced from the minimum of its potential. So if the scalar field was here, there would be no energy in space, and there would be no source for driving the expansion. But if the scalar field is higher on its potential, this gives an energy density in space, and this energy density, if the field initially does not move very fast, is equivalent to like a cosmological constant. And we know that when you put a cosmological constant in Einstein equation, it gives an exponential increase of the size of the universe if you start with zero velocity, let us say. And therefore, inflation is a model in which you say, at some point in some slice in space-time, I have a value of the scalar field phi, which is more or less uniform in space and which has a certain high enough value. This drives an exponential inflation of space, but then the scalar field will tend to move down its potential, although there is a kind of drag force due to the expansion which makes it come slowly down to the minimum of its potential. So classically, the scalar field would like to come down, and that would be the end of inflation, okay? So in general, and that's what people expected at the beginning, if I start inflation here, inflation will always end in a finite time. But what was found, which is a nice idea, is that if you take into account quantum fluctuations, locally in the causal patch of space-time, I mean the Hubble patch of space-time, there are quantum fluctuations. Phi is never really a classical field. There is also the delta phi quantum. So these fluctuations can move the scalar field not only down, but up, okay, in a random manner. Here you treat classic quantum things like a quasi-random classical thing. And therefore, maybe in part of the space, the scalar field will go up a little bit. But if it goes up a little bit, the volume of space it occupies grows faster. And then you find that most of the space most of the volume of the universe is occupied by regions where the scalar field goes up instead of going down. And therefore, from this point of view, inflation will never end in these parts of space because there are big parts of space that always inflate, and there is only a subpart that will go down here. Anyway, it's this idea which led to the idea of one special type of multiverse, which is now to say that if you view what will happen quantum mechanically at the end, you have a very complicated thing. Space, instead of being something uniform where everybody goes down together and inflation at the same time, there are parts of space that still inflate today, and we are a pocket where inflation ceased and things like that. Okay. Now I want to mention also, just to give you an idea of the complexity that one can reach even in this mini superspace, some work that I've been involved with Philippe Spindel, ici présent, as well as with Hermann Nicolai and Mark Hainaut, Hermann Nicolai and Axel Kleinschmidt, who will be present. Hermann will be there tomorrow. No, next week, sorry. So what it is, up to now, I was discussing Einstein's gravity, okay? But if the tendency of the theoretical developments in the 20th century have been to say that Einstein's gravity is only an approximation, a part of a bigger physics which contains many things, and in particular which contains supersymmetric partner of the graviton and more fields. So a simple question you can ask is what happens if you replace Einstein gravity by supergravity? That is, say, gravity where there is not only the usual metric of space-time, but there is also a fermionic brother of gravity, which is called the gravity no. Okay. When you do that, and you do a mini superspace reduction, and when you do pure gravity, then in that case, in pure gravity, you cannot make the reduction I was talking about of the Friedmann universe. Friedmann universe is the simplest thing where there is only one scale factor. So the space is a free sphere that can breathe, be smaller and bigger, but it remains a round free sphere. If you want to do pure gravity, you have to allow the sphere to become anisotropic, like the sphere to be still homogeneous, but in a sense it does not expand or contract with the same speed in all directions. Okay, it becomes anisotropic. Then when you do that, you find that the geometry is described not only by one factor A, which is the scale factor, but by three factors A, B, C, which corresponds to three directions of space that can contract or expand. So instead of a round sphere, you have a general like a rugby ball, although it's not really true. And then you have fermionic partners, which is the homogeneous mode of the gravity no field, because like in the Raman string, the gravity no field can have inhomogeneous modes, but can have also something homogeneous in the full space, and then you need to quantize it and you keep it in this. When you do that, you get an interesting viewpoint on the Wheeler-DeWitt equation, because you don't get a Wheeler-DeWitt equation in the usual type. You get first that the wave function of the universe is not a scalar. It's not now a complex function psi of something. It is a 64 component object. It is a column of 64 complex numbers, which actually is a spinor of spin 12, spin 8,4. And these 64 components, so this index sigma takes 64 values, the wave function still depends on three parameters now, which is the shape of the universe, okay? And this object, which is like a spinor, does not satisfy a Klein-Gordon equation. It satisfies Dirac-like first-order equation, which are the constraints of supergravity, which are first order in momenta instead of being second order in momenta. So instead of a Klein-Gordon type, you have Dirac-like first order equation of this type. That is to say, this column of 64 components of the quantum universe must satisfy something first order in the parameters of the shape. And in front of this, you have gamma matrices, which are 64 by 64 matrices, which are actually the gravity no, and they satisfy the canonical commutation relation of fermion. Fermion satisfies, anti-commutator equal delta function, but when it is an homogeneous mode, it means anti-commutator of the gravity no equal h bar in the right-hand side. And when you take away h bar, this means that this object satisfies a Clifford algebra, and that's why you have 64 components. So already it shows you that even this mini superspace has now a richer spectrum of possibilities. And if you do that for simple supergravity in 11 dimensions, you get like 10 to the 50 different components, 2 to the 160 number of components. It's something so enormous you cannot even compute with it, okay? So mini superspace is not always mini. And so you have the interesting quantum mechanics of this thing, and in particular, we were able to find exact solutions. So this, I did not write the equation. They are very complicated. And also, I did not say it, but it's not that the wave function has to satisfy one Dirac equation. It has to satisfy 4 different Dirac equations simultaneously. In general, there are no solutions to 4 different Dirac equations.
The potentials there?
Yes, so the potential are complicated objects which are essentially cubic in these gamma functions, and they depend exponentially on the betas. And the fact, and these exponential dependence will be important. They are, each coefficient contains exponential of this type, and this exponential will play a very important role later.
And the Dirac equation is the Clifford algebra is with respect to the flat metric.
That's why I did not say that. So here, this metric is something linked to superspace, okay? And in the right-hand side, there is a quadratic form. This quadratic form contains something in the spinor indices which is just Kronecker, but the part which has a signature minus plus plus is this part. So here, this metric is a metric in superspace of the 3 betas, which is Minkowskian. So there is one direction which has a minus sign, and this direction is the volume of the universe, because we know that always in Einstein equation, in Einstein-Lagrangian, if you try to, the kinetic term linked to the volume change is negative, okay? There is a wrong sign in Einstein equations for the volume mode, and for the modes of deformations, it is positive. That's why this metric has signature minus plus plus. And so now, why do we do that? Because this is I mean, the idea, these are academic studies if you want, but to try to understand what happens at a big bang or at a big crunch, and I will mention more of this. First, although these are very complicated equations, we could find a few exact solutions, and in particular, one solution which is here rewritten in terms of, by the way, beta 1, beta 2, beta 3 were the logarithm of the 3 scale factors ABC, okay? Now I wrote the solution again in terms of the ABC, the scale factors. And the most important factor here is this thing, okay, which had been found before for mini superspace without supersymmetry, but here we have decorated by this. So it is remarkable that you can find this solution. And if you try to think physically about what this solution means, so this is a really quantum universe which has a wave function. The wave function essentially is centered around a size, physical size of the universe, which would be 10 minus 33 centimeter, the Planck length. But this universe, in a sense, is oscillating a little bit, like changing its shape, but not changing its volume, essentially. And this is like a quantum ground state of the universe sitting there in superspace, waiting for, it's like the cosmic egg of Indian philosophy.
So you don't, but you still have time, or it's just one of?
There is no time in Einstein equations, Time.
That's reason. When you say that it changes the size, you refer to something.
That's true. That's true. That's true. We'll discuss that. Okay. We will see better things what I meant by this time. Okay. It is the direction in beta space which corresponds to the minus sign in the quadratic form.
I thought that matter could play the role of time in some cases.
Yes, sure. But here we have no matter. It's pure supergravity. Yeah, if we want clocks, the answer to the problem of time is that you have to put clocks, you have to couple gravity to a clock, as discussed by Joost, Kiefer. This is a problem I don't want to discuss here. What I want to say is this is an exact solution, okay? But then there are also continuous, this is like a discrete spectrum. So there are a few solutions. We will see that it's like a Kleiner equation in a potential, in a sense, which is kind of confining, okay? So you expect maybe a few discrete modes, but there are also like continuous spectrum modes. And these continuous spectral modes have several remarkable features that features we are interested in for physics, because they exhibit a hidden hyperbolic Kac-Moody structures. Okay, so I won't discuss here what it means, but this is something. This is where E10 enters. And a second interesting thing is here we are quantum and we put fermions in, so we can really discuss the effect linked to quartic terms in supergravity. You know, supergravity, the curse of supergravity is that it works because there are quartic terms in fermions, but people never write down the terms quartic in fermions. They are too complicated. Here, we wrote them down and we solved the thing. And then we found something interesting, which is that these fermions, they create an energy density which increases very much when you try to reduce the volume of space to 0. So it's something which blows up and which has a sign, negative sign, such that it creates a bounce. That is to say, if you classically you try to crush the universe to a point, there is a repulsive force which makes it bounce to bigger size. So here it shows that quantum effects in cosmology and fermionic effects can lead to what people were looking for, which is avoidance of the Big Bang singularity. Okay. More precisely, this is a picture of the. So here we are in. This is the superspace. So it's the mini superspace of this triaxially squashed 3-sphere. So this is a 3-sphere which has been squashed in 3 directions. So I have 3 parameters. I take the logarithm of these 3 parameters, and these are beta 1, beta 2, beta 3. If I take the sum of the 3 parameters, which is the volume of the universe, it will be this slicing here. So it's what I call time here, okay? Time means the volume of the universe, because finally in expanding cosmology you can say the time is the size of the universe, okay? And what happens is that these things here are regions where the potential is large and positive. And therefore, in a sense, if you have a wave function here, it will tunnel. I mean, one natural boundary condition says it's like a wall. It's like a potential wall, and the wave function can decay exponentially in this wall. So the wave function is confined here, okay? Then what happens is here, because of the fermions, there is in general also a wall, okay? And in fact, classically, if you solve now the equations of motion of this classical system with the fermions put in, as classical thing, you find that the trajectories are chaotic, and they try to go up in time, which means going to 0 volume, but they bounce to bigger volume again. But when they go to large volumes, we know what happens, because if the universe tries to go to large volumes, it recollapses. This is what Friedman had found long ago. A closed universe, because of the curvature of space positive, means when you go to large volumes, you want to recollapse to small volume. And here, therefore, you see you are confined in all directions. You try to go to small volumes, you bounce. You try to go to large volume, you bounce. You try to go to very anisotropic shapes, you bounce. And therefore, you have like a bottle effect where the wave function is confined in a potential in all directions. And then there is a question that we speculated. Does it mean that the quantum states here are discrete? Although we found something that in some approximation are like wave packets. We don't know. This is a mathematical question which was well posed. I asked it to Sergio Kleinerman, but he has not reacted yet. Now, in my title, there was, I still have 15 minutes, so it's okay, I don't need to hurry. I said back to Einstein. Yes, so let's remember Einstein's vision. The last words of Einstein in his life, okay, in front of an audience, where there is much reason to be attracted to a theory with no space and no time. By the way, all these, when I say these are the last words of Einstein, thing like that, what happened is that first there are people still alive who attended the seminar, and sometimes I ask them questions about that, what Einstein wrote on the blackboard and things like that, although memory is fading away. But John Wheeler, who had organized the thing, was taking notes all the time. And then there is a text written by John Wheeler of the verbatim things that he could take of Einstein. So these words, like no time, is from Wheeler transcript. Okay, so yes, because now I want to mention as a possible speculations some work that I have been working on for some time now, more than 10 years, with Hermann Nicolai, Mark Hainaut, Axel Kleinschmidt, Philipp Spendel, it's a conjecture, it's a big conjecture, which is based on the following thing. We just mentioned here that for supergravity ordinary supergravity in 4 space-time dimension, there was some hyperbolic Kac-Moody structure. Actually, the first Kac-Moody structure we found was by taking string theory reduced to low energy, so all string theory models in 10 dimensions and supergravity in 11 dimensions, and all of them, when studying what happens near a cosmological singularity. So what we did was first classically, we take Einstein's equations, 10 dimensions, and you look what is the structure of a general gravitational field near a cosmological singularity. Okay, it's a well-posed mathematical question that we answered by physical means using the Belinsky-Halatnikov-Lifshitz approximation, which are in Landau-Lifshitz. And the surprise was that they are chaotic, but that this chaos is linked to a billiard motion in the Weil chamber of an hyperbolic Kac-Moody algebra. And actually, this thing here, this upper part of this diagram, going up there is going towards the singularity. And this thing becomes nicely 3 walls. You see 3 hyperplanes. And these 3 things, the equation of these 3 things are linear forms in beta 1, beta 2, beta 3. And these linear forms are called the simple roots of an algebraic, of a hyperbolic Kac-Moody algebra. And for E10, you find 10 walls like that in a 10-dimensional Minkowski type space-time with one negative direction which corresponds to the total volume of this 10-dimensional geometry, and 9 directions which are the anisotropies of this 10-dimensional geometries, homogeneous geometry. And then you have this strange appearance of E10. But then we found, E10 is above E8. Many people know that the Cartan classification of Lie algebra stops at E8 among exceptional group. If you go to Kac-Moody algebra, you can go to E9 and E10, and this is the last hyperbolic Kac-Moody algebra, although there are things called E11 which are not hyperbolic anymore, but Lorentzian. Anyway, and then we found that there was a big analogy, a technical, precise analogy between the equations of motion of supergravity in 11 dimension. If you look at them locally in space and you say that essentially the functions depend mostly on time because you go to a singularity. So you expect that your functions become mainly functions of time, and space will be like a corrections. But you can take into account the spatial dependence by successive approximation, and you find that this beginning of this expansion, infinite expansion, is in precise correspondence to the motion of a massless spinning particle on an infinite dimensional coset space, which is E10 group divided by K of E10, which is the compact subgroup of E10. So just words to say that there is a hint that maybe when we, and then we made the conjecture, and before us, we should say that Oregano had mentioned E10 in a different context, and Peter West at the same time had mentioned maybe E11 should be better. Anyway, E10, we find only E10 in what we do. But the basic point is the following here. The idea of this conjecture is that the usual description of gravity and quantum gravity is that it should be described by fields, a gravitational field, and gravity in space, the 3 form, and then if you have extended objects, in string theory, M theory, all the extended modes. But when you go towards a space-time singularity, this description of a space which evolves in time should be replaced by something completely algebraic now, which is a point in moving in an infinite dimensional coset space. So what we are saying in a sense is that we should replace, let's say, Wheeler superspace by, which was never well defined, okay, by this better defined space, which is a coset space, a symmetric space, an infinite dimensional group divided by its maximally compact subgroup. And in principle, you can write the equations of motion for geodesic there. And what we are saying is that if you take the quantum version of that, that is to say, if you write the quantum mechanics of a spinning particle in this infinite dimensional thing, this should represent the full dynamics of the universe and its content. Okay. Evidently, it's a big conjecture. More precisely, if we put the idea of Hull and Townsend of dualities in string theory, you find that the wave function should move not only on the coset space, but on the coset space discretely quotiented by E10 of z, which means that this thing is an automorphic form, should be an automorphic form propagating on this space with some periodicity properties with respect to an infinite dimensional discrete subgroup. So it is a conjecture that only small fragments of it worked it. In particular, I wanted to put them, like for instance, a drastic approximation of this, which is the billiard approximation, has been particularly studied by Axel Kleinschmidt and Philip Flagg present here. Anyway, it's a big conjecture, but this is just an idea that maybe this would be, it would replace quantum gravity to have this thing. So it was suggested by this approach. And then it would be purely quantum, okay? Because this would be the equation of the universe, except that probably there is Dirac-like equations that were only partially written for this. Let me come back to quantum cosmology. First, I want to say that I mentioned several results derived by physicists, okay? But many of these results, they have been obtained only by coarse approximations, and there is room here for really a lot of mathematical progress, but not only mathematical, because for me, one of the most important problem which is unsolved is the problem of the back reaction of quantum fluctuations. When you have a classical universe and you have quantum fluctuations, you can treat the quantum fluctuation as linearized thing, okay? But at the next order, you should say, but they contribute to the energy that drives the expansion of the universe. So what do I put in the right-hand side of Einstein's equation? And the usual answer you find in textbook is that you write in the right-hand side of Einstein's equation the vacuum expectation value of T mu nu for the field. It is known experimentally to be wrong, okay? That you can, there were quantum gravity experiments that showed that it's not the good thing, okay? And in cosmology, it's even worse. What I want also to insist on is, even if we forget about the most speculative parts of quantum cosmology, like what happens near singularities, potentially, what happens eternal inflation, the theory of linear quantum cosmological perturbation, a la Muranov-Chibisov, show that our local universe, the Earth, the Moon, the Sun, the galaxy, is a priori smeared in a quantum superposition, because this is just, if I follow just quantum mechanics, nobody is, except if you want to say the first mouse that existed on Earth has reduced the wave function of the universe, you have to think that this is supposed, it's not very clear, supposed to be the galaxy with the Earth being all smeared out around the Sun, and this is the same galaxy. We are in a superposition of all these galaxies on top of each other in a Hilbert space, evidently. Okay, and now let me finish by summarizing Everett's view for people who are not familiar to this, because he expressed in view to his letter in May 57 to DeWitt. DeWitt was the first one to take seriously, really to the end, what Everett had written. And what is interesting is that, because DeWitt said, you are talking about splitting universes, okay? But I don't feel any split. Therefore, your theory is wrong. And then the answer of Everett was, yes, it's like the basic criticism against Copernicus. People said at the time of Copernicus, it is absurd to say that the Earth is moving to 1,000 kilometers per second and things like that. We don't feel the motion of the Earth. Okay? Common sense says that the Earth is not moving. Therefore, the Earth is not moving. And Galileo had to invent a physical effect. He had to make an ad hoc principle, the relativity principle, and give a beginning of experiments to show that when you are in a moving reference frame, you don't feel the motion. Okay? So you needed to prove within classical mechanics that there is a mechanism which makes that our experience will not feel the motion of the Earth. And the answer of Everett was that he's saying, my mechanism is indeed, so he told DeWitt, do you feel the motion of the Earth? And he says, the theory I've developed is in full accord because within my theory, it is possible to show that no observer would ever be aware of any branching, okay? And then he continues saying that in his view, there is no necessity of any transition from the possible to the actual. just to clearly state what he said about this thing, that all branches, because many people say, he never said many worlds first, okay? He used the word sometimes split, amoeba branches, and the reality is everything. None of these parts of the wave function are supposed to be more real than the other one. So we just take as reality what is pure Schrödinger equation. You know, the cat, both dead and alive, except that if we are the cat dead, we don't feel alive. If we are the cat alive, we don't feel dead. Now, personally, I find Everett's attitude as the most rational and economical, contrary to what people tend to think, of way of thinking about the quantum world. It is consistent both with Kant's philosophy, and this is what I have called le quantique du quantique, so it's better to keep it in French because there is a joke there. And this is a citation of Kant. Hitherto, it has been assumed that all our knowledge must conform to objects. That is to say, the usual epistemology before Kant was to say there are real objects that exist, and the aim of physics is to describe this reality, okay, that pre-exists. Why Kant said, let us try to see, there is a T missing, whether we may not have more success in the task of metaphysics by assuming that objects must conform to our knowledge. That is to say, the notion of objectivity comes from the theory, from physics, okay, and mathematics. And this is what Everett did for quantum mechanics. And also, this is along to Einstein's GR, general relativity inspired epistemology. It is only the theory which decides what can be observed. And if you assume, like von Neumann assumed, and Everett heavily assumed, psychophysical parallelism, that is, if we don't assume there is something totally extraneous to physics and reality, which would be the mind or whatever, but we are embodied also, whatever be our view on ultimate reality, we are embedded in reality, in everyday thing. Everett's view is no more paradoxical than the other paradox that remain, which is the famous many times or many minds problem. Because if you think about before Everett, before quantum mechanics, whatever, time is, there is no now. This was a question. There is no now in physics, okay? And also, if mind is something, an emergent structure, why am I me and not Klaus, for instance? And these are mysteries, and any theory has never solved them, okay? Just approximation. And so Everett's idea is adding just a little bit a paradox of the same kind, but not worse, okay? It's at a metaphysical level. To conclude, let me just show one of the last sentences, the last words of Bryce DeWitt on Everett, because this is in his last book, and he died just after the publication of this book, which is the following. Everett's interpretation has been adopted by the author out of practical necessity. He knows of no other. At least he knows of no other that imposes no artificial limitations of fuzzy metaphysics while remaining able to serve the varied needs of quantum cosmology, mesoscopic quantum physics, and the looming discipline of quantum computation. Thank you.
Jörg, so could you now tell me what Everett's interpretation is?
I never use the word interpretation.
Or Everett's view?
Everett's view is...
branching.
No. Everett's view is you take Schrödinger's equation. Yes. Stop. That's it.
What about the... Is it a knowledge or an object?
Sorry?
You said, I don't know anything about Kant, but you mentioned that he was making a distinction between objects and knowledge.
Yes.
So is Schrödinger equation, from your point of view, an object that exists and we have to look at it? Or is it a knowledge we have from the universe? Or I have an unclear idea.
The meaning of this citation is, for me, knowledge is Schrödinger's equation. I assume this is a true equation. And then the aim of Everett is, let's take this equation and then deduce from it what is the notion of object in the quantum world. Yes. That is to say, of objective reality. And what you come out is after doing an experiment like the Schrödinger cat, that the reality is a superposition, okay? Serge Haroche is doing superposition. So one faces this.
May I ask Klaus if he believes or not, Alfred?
Do you believe in Schrödinger's equation?
Yes, I believe in Schrödinger's equation, of course, but I have a different interpretation of what it means. In a sense, and Jörg will also agree, the Schrödinger equation gives a relation between a subject and an object. We are guessing about things using the knowledge which we have about the past and guess about the future.
So we means we monkeys or we human beings?
I.
You, Klaus have.
It's in a sense very solipsistic.
Yes, okay, there is, one cannot disprove solipsism.
But Kant also had a
I
very
don't know what you mean. I mean, we make consistent guesses. Klaus and I guess the same way, and David too. Only you guess otherwise.
No, I'm not sure. David, you can ask David, but...
No, I think the philosophical part we should postpone.
yeah, are there technical questions?
So I an experiment in the lab using this point of view.
Yes.
How do you do it? Say quantum optics, it's quantum.
Yeah, you use decoherence, okay? Yes.
I have a technical question. Is time unobservable in this quantum universe?
No.
Can I observe it?
Well, you mean time does not exist? Yes, here.
But you said the matter field can play the role of time or maybe A, and that's part of the wave function arguments.
You can, if you want, for instance, if you were Bohrian, I mean, you can define, if you want, when you have the wave function that depends, when you have a wave function that depends on these three variables, you can look at the value of the wave function when the sum of the three variables is equal to 0 or 1 or 2. That would correspond to considering what happens, space with a fixed volume, okay? Which is a definition of time in cosmology.
If I measure the volume of the universe, do I freeze it?
Can you measure the volume of the universe?
Suppose I could. Would the universe freeze?
Will you freeze them? Sorry. Freeze time, you mean?
Would I collapse the fixed volume of the universe?
But this is like the usual quantum mechanics. If I have it's not different. Any question like that, you know, if you want to say there are observers, super observers, or whatever, they are observers, you can do that. This question is for them, okay? Here, I want to ask questions about what is physically observable, okay? This is the aim here, okay? But this we have seen, like, just for a few cells in the human brain how complicated it is to have this. So now if we want the whole community of astronomers observing the CMB, I mean, we have to think that this is part of the wave function. So the wave function is complicated. And this part, as soon as it decoheres completely from neighboring parts of the wave function, it evolves separately from that. And then for all practical purposes, we come back to von Neumann collapse. There is no, I mean, Everett plus Z plus Hep plus Yos. No, you introduced after the first model of decoherence. What you explained was the first precise computation.
Answer to all questions
yes.
at T.
Yes. Yes, if we want to have T.
Thank you.